Welcome to this presentation on the discretization of continuous time systems. We would solve a standard state space equation using exponential of a matrix. We will evaluate it at sampling instants. We will use zero order hold input to arrive at discrete time equivalent. We will conclude this talk with an example. Recall the exponential of a matrix. F is square and constant. This is the derivative of this, and we want to solve this continuous time state space system. First, we will rewrite it as follows. We bring this f of xt to the left hand side. Then we pre-multiply both sides by exponential minus ft. So the left hand side becomes this, where we have multiplied by exponential minus ft, multiply the right hand side also. You can write it as follows. Look at the left hand side. You can write it as total derivative. If you differentiate this first with respect to x, you get this. Second, we differentiate this term with respect to t and we get this term. Here we have used this equality. Okay, the right hand side is kept as it is. What do we do with this? We will now integrate both sides from t0 to t, where t0 and t are arbitrary at this point. So because it is a total derivative and you integrate it, when you integrate it you get this value at final time minus this value at the initial time equals, this is just written as an integral. We will not simplify it now. We take it to this side, on the right hand side, you get this, and then pre-multiply by exponential f of t on both sides. We obtain x of t equals exponential f of t minus t0, x of t0 plus, now exponential ft is taken inside, we get this expression. We will simplify it further. We are interested in the solution at the sampling instants only. Recall why we are doing it. The controller is a discrete time system. It is interested in knowing about the plant at the sampling instants only. So what we will do is we will substitute Tn in the place of t0, Tn plus 1 in the place of t. Okay, when we do that, x of t becomes x of Tn plus 1, because in the place of t we are putting Tn plus 1. Similarly, we simplify every term. The first term, it is Tn plus 1, t0 becomes Tn, t0 becomes Tn, and the integral goes from Tn to Tn plus 1, and we obtain this expression. Note that tau is a dummy variable and hence it is not changed. Okay, let us start with this, and we will make the assumption that u is piecewise constant. Remember, we also called it the zero order hold. So as a result, what we do is we hold the input variable u constant over the interval Tn to Tn plus 1. And what value is chosen? The value of u taken at the initial time. Remember, Tn is the initial time. Whatever value of u at Tn, the same value has to be used throughout this interval. Whatever value u takes at time instant Tn, that is at the beginning of the interval, should be used throughout the interval. Next, we will assume that the system is sampled at a uniform rate with a period Ts, which is equal to Tn plus 1 minus Tn. Recall that this is called definition operator. So we are defining this new variable called Ts as follows. So the solution to our state space equation becomes the following. There is no change in most places, only here it changes f of Ts, and there is no change in the second one, except that now u is constant over the interval Tn to Tn plus 1, and it takes the value of u of Tn because of this assumption. So here is the solution that we derived in the previous slide. Now we will call exponential f of Ts as A and B as this whole thing inside this square bracket. One can show that this is equal to this expression. I would want you to do this. A and B are constants, and so the solution becomes A times x of Tn plus B times u of Tn. Okay, what else can we do next? Remember, we have constant sampling rate, constant period of sampling. So as a result, we can simplify this further. We will use the sampling number. We will write this as x of n plus 1 axn plus bun. So here we take the t0 as 0 and then x1, x2 and so on. So this index n refers to the sampling number. This is the 0 order hold equivalent of this continuous time expression. Recall the assumptions that we made to derive this. Input is constant over every interval and uniform sampling. Recall that we also have an assumption on f, namely f is square and constant. So here is the summary of our result. This is the continuous time expression. This is how A and B are defined, and we obtain this continuous time expression. We obtain discrete time expression here. We will now present an example. Calculate the 0 order hold equivalent of the following system with the sampling period as 1 second. Here is the continuous time system given to us, and this is f and this is g. Recall that we already calculated for this example earlier. So exponential f of t is this expression which is already calculated. So A is exponential fts. All that you have to do is wherever t is there, you put ts, and ts is 1 second, you substitute 1 here. Of course, we assume that all time units are in second in this problem, and when I substitute the value for exponential minus 1 and simplify, I get this matrix on the right hand side. So A is calculated. Let us next calculate B. Recall the expression for B. It is 0 to Ts. In the place of Ts we have put 1, and then we need to substitute for f and g. So this is exponential f tau d tau into g. G is 0, 1. Let us first integrate this. What we do is do a term by term integration. So the integral of 1 is tau, integral of minus exponential minus tau is plus exponential minus tau. So we get this expression, and it has to be evaluated between limits 0 and 1, and it has to be multiplied by the vector 0, 1. What we will do is we will first multiply this out and then take the limits. So when I multiply this out, this 1 will pick the second column, I get this. This column will be made 0 because of the presence of this 0 here. So I have to evaluate this at tau equals 1 minus the same expression evaluated with tau equals 0. and it is easy to see that you get this 1 plus e minus 1 is what happens when you substitute this equals 1. When you substitute tau equals 0, this term will go away and you get 1 here, which is this. So similarly here you get exponential minus 1 minus, of course, because of the sign here, and then minus the value obtained at tau equals 0, which is 1. When you simplify it, you get these values. With this, we have come to the end of this presentation. Thanks for joining.